The vast frozen expanse of Antarctica, a continent often perceived as static and unchanging, is showing profound signs of stress. Recent satellite imagery has brought a startling feature into sharp focus, a massive fracture snaking across one of its critical ice shelves. This immense crack, a powerful symbol of a continent in flux, has captured the attention of scientists and the public alike. It raises an urgent and fundamental question. Is Antarctica, the Earth's southernmost landmass, beginning to split apart? The scale of this fissure is difficult to comprehend, stretching for many kilometers and plunging deep into the ancient ice, a stark visual reminder of the powerful forces at play in this remote and vulnerable part of our world. While the dramatic sight of such a crack might inspire images of the continent itself cleaving in two, the reality is more complex. Antarctica is not splitting. Instead, what we are witnessing is a process amplified by a changing climate. The crack is forming in an ice shelf, a colossal floating platform of ice that extends from the land-based ice sheet out over the ocean. These shelves act as a natural break, holding back the immense glaciers that lie behind them. The appearance of such a significant fracture is a clear indicator that this braking system is losing its strength, a worrying development for the stability of the entire region. The news from the Southern Hemisphere has been particularly active lately. Throughout late 2024 and into the early months of 2025, satellites have documented unprecedented events. On December 25th and 26th, 2024, a record-breaking surface melt was observed, affecting over 3% of the entire Antarctic ice sheet's surface. This extensive melting creates ponds of blue water on the surface of the ice, as seen on the Amory ice shelf in January 2025. This water can then seep into smaller crevasses, exerting pressure that can widen them into the massive fractures we now see, a process known as hydrofracturing which threatens the shelf's integrity from within. This is not an isolated incident but part of a larger, more concerning pattern. The continent's ice shelves, particularly those on the Antarctic Peninsula and in West Antarctica, are retreating and thinning at an accelerated rate. The crack is a symptom of this broader ailment. It represents a critical point in the life of an ice shelf, the prelude to a massive calving event where a piece of ice, sometimes the size of a small country, will break away and drift into the sea. This process, while natural, is happening with increasing frequency and on a grander scale, driven by the warming of the atmosphere and, more critically, the oceans that lap at the ice's edge. Understanding why these immense cracks form requires looking at a combination of natural cycles and human-induced pressures. Ice shelves are dynamic systems. They are constantly in motion, flowing slowly from the land towards the sea. As they stretch and bend over the ocean, stresses build up within the ice, naturally creating crevasses and rifts. This is a normal part of their life cycle, a push and pull that has been happening for millennia. For an ice shelf to remain stable, the amount of snow accumulating on its surface must balance the amount of ice lost through melting from below and the calving of icebergs from its front edge. However, this delicate balance is being profoundly disturbed by climate change. The primary culprit is the warming of the ocean. Warmer ocean currents are increasingly circulating beneath the floating ice shelves, eroding them from their most vulnerable point, their underside. This basal melting thins the ice, making it weaker and more susceptible to fracturing. Think of it as the foundation of a house being slowly washed away. Eventually, the structure above is bound to crack under the pressure. This unseen melting is a relentless force, gradually undermining the stability of even the most massive ice shelves. Simultaneously, rising air temperatures are impacting the ice from above. As we saw during the record melt events of late 2024, warmer summers lead to the formation of extensive meltwater ponds on the ice surface. This water is darker than the surrounding snow and ice, so it absorbs more of the sun's energy, which in turn leads to even more melting. This meltwater then pools and seeps into existing crevasses. Because water is denser than ice, it exerts immense pressure as it fills these cracks, forcing them to widen and deepen, sometimes cutting right through the entire thickness of the ice shelf. This process can rapidly accelerate the disintegration of a shelf. Scientists have been clear about the connection. Dr. Alison Banwell, a glaciologist specializing in ice shelf mechanics, has stated, "While calving is a natural process, the frequency and size of these events are clear indicators that the system is out of balance. The warm water eating away at the base of the ice shelves is a direct consequence of a warming planet, making the ice far more prone to the kind of large-scale fracturing we are currently observing. This combination of melting from above and below creates a powerful 1-2 punch that is pushing Antarctica's icy fringe towards a tipping point, a reality confirmed by continuous satellite monitoring. The culmination of a massive cracks journey is a calving event, one of nature's most spectacular and powerful displays. When a rift finally cuts across an entire ice shelf, a new iceberg is born. These are not small chunks of ice. They can be colossal, often measured in thousands of square kilometers. In May 2024, an iceberg named A83, roughly the size of Portland, Oregon, broke away from the Brunt ice shelf. Another famous example, A68, which calved from the Larsen C ice shelf in 2017, was one of the largest ever recorded. The detachment of these giants reshapes the coastline of Antarctica in an instant and sends a new floating island out into the Southern Ocean. The journey of these mega icebergs is tracked closely by scientists using satellite technology. As they drift on ocean currents, they begin a slow process of decay. They are battered by waves, which can cause smaller pieces to break off, and they melt as they travel into warmer waters. The A68 iceberg, for instance, survived for over 3 years before it finally fragmented and melted away near the island of South Georgia in 2021. During its peak melt, it was releasing an astonishing 1.5 billion tons of fresh water into the ocean every single day, a massive and sudden injection that can have significant local and regional effects. The immediate impact of such an event is often ecological. A massive iceberg can act as a physical barrier, blocking the established foraging routes of penguins and seals, potentially impacting the survival of entire colonies. The calving of A83, for example, temporarily blocked sea access for the emperor penguin colony at Halley Bay. Furthermore, the massive release of cold, fresh water alters the local ocean environment. It changes the salinity, temperature, and nutrient levels of the surface water, which can disrupt the base of the marine food web, affecting everything from phytoplankton to the great whales that feed on them. However, the scientific story is not entirely one of destruction. The melting of iceberg A68 revealed a fascinating and previously undocumented phenomenon: the immense volume of fresh water and the nutrients, like iron, that were locked within the ancient ice created a halo effect of life around the melting giant. This influx of nutrients supported huge blooms of phytoplankton, which in turn drew in other marine life. It also led to deeper mixing of the water column, which scientists believe may have increased the amount of carbon being absorbed and stored in the deep ocean, highlighting the complex and sometimes surprising ways the Earth system responds to change. The calving of a single iceberg, no matter its size, does not directly raise global sea levels, because the ice was already floating in the ocean, displacing its own weight in water, much like an ice cube in a glass. The real danger to our coastlines comes from what happens next. The ice shelves, like the Amory ice shelf that holds back the vast Lambert, Meller, and Fisher glaciers, are critical buttresses. They act as a dam, slowing the flow of the land-based glaciers behind them. When an ice shelf collapses or is significantly weakened by a major calving event, this braking effect is lost. Without the protective barrier of the ice shelf, the grounded glaciers behind it can accelerate their slide into the ocean. This is new ice, previously stored on land, being added to the sea. It is this process that directly contributes to global sea level rise. Every major fracture and calving event is therefore a warning sign that this acceleration could increase. Scientists estimate that the glaciers held back by the Amory ice shelf alone contain enough ice to raise global sea levels by several meters. Its stability is therefore a matter of global concern, and the record melting observed there in late 2024 is a deeply worrying sign. Fortunately, we are not blind to these changes. A fleet of satellites, including NASA's Landsat program and Europe's Sentinel missions, constantly watches over Antarctica. We use a variety of sensors to monitor ice velocity, thickness, and surface melt year-round, explains Dr. Helen Fricker of the Scripps Institution of Oceanography. This continuous stream of data is vital. It allows us to see these processes unfolding in near real time and helps us improve the models we use to predict future sea level rise. This constant surveillance is crucial for understanding the speed at which these changes are happening and for providing policymakers with the information they need. The future of Antarctica's ice shelves is inextricably linked to our global climate trajectory. The science is clear. The more we warm the planet, the more we will destabilize these vital icy barriers. The massive cracks are not a sign the continent is splitting, but they are a clear message that it is responding to the heat we are adding to the Earth's system. The continued monitoring by scientists provides a crucial service, but the data all points in one direction. The fate of the ice, and consequently the shape of our future coastlines around the world, depends on the choices we make today to curb global warming and protect these magnificent and critical parts of our planet.